Okay, so please switch on your mics. So yesterday we were discussing that for one dimensional monatomic lattice, the dispersion relations are given by these things. Okay, and there is a cutoff frequency, maximum frequency. Okay, and cutoff frequency just now discussing is occurs. Let me draw again. Okay, so cutoff frequency. Okay, this is the region pi by a to minus pi by a. So I told you at the boundaries when your k is equal to pi by a, okay, plus minus pi by a, and k equal to pi by a, and then that case lambda equals to 2a, okay, and that lambda is the cutoff frequency, your cutoff wavelength, okay, and that cannot be less than 2a. So lambda cutoff is, you can remember that one, lambda cutoff is equal to 2a. Okay, now I want to discuss that BR is the frequency. Now we are limiting ourselves only up to this region, and I told you this region is billion John. Okay, this region is billion John. Okay, so let me discuss it more in detail. Why it
Sir,
is called billion John? Okay, yes,
sir, that same I'm asking. What is brilliant zone?
yeah, I'm discussing now. Okay, I'm
Sorry.
discussing.
Sir,
Okay,
this cutoff frequency for one dimensional monatomic is 2a, na?
but two way
Lambda equals to.
cut off wavelength. Yes.
Okay.
Okay, so let me now discuss what is your billion John, or we have to define, okay, formally the what is billion John. Okay, so let us discuss. So now, okay, so we know the dispersion curve. Okay, and yesterday we have drawn this omega versus k relation. Okay, this omega versus k relation, and we have plotted our graph. We told this is our graph. Okay, okay, so this is my 0, this is my pi by a, okay, this is 2 pi by a, okay, this is 3 pi by a, this is 4 pi by a, okay. Similarly here this is minus pi by a, minus 2 pi by a, okay, minus 3 pi by a, minus 4 pi by a. Okay, now I told you that any wave vector k, okay, k dash, okay, it is equal to k plus 2 pi by a. Okay, if in the expression of frequency, if I calculate omega equals to k dash, okay, where k dash is equal to k plus 2 pi by a, that will come out as omega k, isn't it? If our expression of sine k, if I put k equals to k dash equal to k plus 2 pi by a, okay, so that will be always equal to k. Are you so what I'm
Yes,
saying?
sir. It is clear.
Okay, okay, so that means this k and k dash, they are indistinguishable, they are not on any new vibrations. Okay, so k dash and k are indistinguishable, indistinguishable. Okay, so any k I take here, for example, I take this k, this is my k, okay, and here I say take k dash, okay, k dash, where k dash is equal to k plus 2 pi by a. Both at both this point my frequency is same. Okay, that's means the k is periodic. Okay, so any properties of the crystal which is a function of k, that will be also periodic because k is periodic. Okay, now Now I told you this pi by 2a minus pi by 2a region. Okay, this is the region where your k values are unique. Okay, this is the region where your k values are unique. Okay, in this region. Okay, or you can say this is the region. Okay, if you take the k values of this one and we repeat itself, okay, you will get all repeating values. Okay, so now let me define what is your in definition, what is your actually billion John is called. Okay, so before I calculate the
Sir,
definition, wait. Just yes. So
sir, I have some internet work problem. Sir, can you explain the graph once, please?
so I'm again explaining. So this is my omega versus k curve. Okay, this is the sine k mod of sine k graph. Okay, so we have plotted this one, and I told you like yesterday that your k is periodic function. Okay, and same omega is also omega k is also periodic function. So if you take k dash or k plus 2 pi a, both are same k value, both need the same frequency. Okay, if you put these values in sine k, you get omega k dash equal to omega k. That means this k value and this k dash k plus 2 pi a, they are same. Okay, now you can check this one also by putting our functions. Okay, our functions was yesterday what un was a iota k a and a minus omega t. Okay, so if I take u dash, okay, u dash k dash, okay, where k is what, so a, if I use this one k, where my k dash is k plus 2 pi by a, okay, k into na minus omega t. Okay, if I solve this one again, I get e power, okay, 2 pi by iota 2 pi by a. Okay, a cancel, so iota 2 pi n, and I will get here exponential k na minus omega t. Okay, and e power iota 2 pi is nothing, it is 1. So again I get a equals to iota k na minus omega t, that is my un. Okay, so these functions are same. Any function, any amplitude value, you take on k and you take on k dash, both are same. Okay, that's why I told k are interchangeable. Now what is your billion John? Okay, so now because k values are repeating, so I don't need to take all the k values, so I will restrict my graph only up to pi by a to minus pi by a. Okay, so now I have this graph. Okay, omega versus k graph. Okay, so this is my pi by a. Okay, and this is minus pi by a. Okay, so I only need these k values. Okay, I told this is your billion John. Okay, this is your billion John. So now I can define the billion John definition, right? Definition billion, and I will try to connect with this crystal also. Okay, billion John. Okay, a region of space, a region of space. Okay, a region of space that contains okay, a region of space that contains all the unique solution, okay, a region of space that contain all the unique solution of the wave function. Okay, so this region which contain all unique k value, after that what are you getting? That is repeating k values. Okay, that are not new things. The region of space that contain unique k solutions of k value, that is called billion John. Okay, let me define it some other way also. Okay, So, or you can define
Sir,
you billion.
Yeah.
हाँ बोलिए.
sir, ये wave function means wave function which is means lattice का
हाँ
wave
लेट
function या
लेट वेव फंक्शन. अभी हमने क्या लिख रहा था, अभी हम लिख रहे थे ना, यूएन लिख रहे थे ना, यूएन. ओके,
हाँ,
UN, that is amplitude function. Okay, that's
okay.
what I'm talking. Okay, okay. So a regional space contain all the unique solution. That means I'm asking solutions. Any equation, we have equation, and we are getting the solution of those equations. Okay, so the only solution equation where only unique solutions. The regional space which contain unique solutions, that region is called your billion John. Okay, or let me give me one more definition. Unit cell of crystal. Okay, about which unit cell of crystal about which, okay, wave vector, okay, keeps on repeating, repeating. Okay, that is the one thing. Okay, now that is the definition of billion John. Now let it me what you have studied in your crystal structure, how in crystal structure we define billion John. Okay, so we know that we were working on direct lattice. That's why I draw this chain of atoms. Okay, and this was my what? This is my direct lattice. Okay, these are my atoms. Okay, and the distance between this atom I told you A. Okay, now if I take the Fourier lattice, reciprocal lattice, or if you go in K space, which is the inverse space of this X. Okay, so I can draw. So one dimensional crystal, the reciprocal crystal is also one dimensional. Okay, this is also one dimensional. Only the distance between now 2 points, okay, is 2 pi by A. Instead of having pi by A, the distance between 2 points, okay, distance between 2 points, this distance, okay, this distance is 2 pi by A. Okay, now if I plot a unit cell here, that is called Wigner-Lattice unit cell. Okay, shall I erase this one?
Sir, second one you have drawn that is in reciprocal lattice, no? First one
Yes. This is your reciprocal lattice. Okay.
Sir,
Just
I
let.
have doubt
पूछिए.
in this billion John first definition. Unique solution means they will not repeat, no?
So no, you repeat means the other solution will not be new. Okay, they will be same thing. If you go k dash plus k plus 2 pi by beyond this region, whatever you will get k, you already have that values here. Okay, suppose some value is here, that already you're getting here, this k value. So any solution that you're not getting the new k, already you whatever you got of old k, that is repetition of those k's values. Okay, I'm discussing physics. Let me complete this one. Okay, so this is your billion John, a region of space that contain all the unique solution of the wave function. Okay, now I told you I have a reciprocal lattice. Okay, so this is my reciprocal lattice. Okay, so I told you this is 2 pi by A. This distance is 2 pi by A. Okay, now if I draw a unit cell, okay, now these are my atom and these are my neighboring atom. Okay, now if I divide, if I divide distance, okay, and plot a unit cell, okay, this is unit cell, okay, by dividing the nearest neighbor distance. There are two in this one dimension, these are nearest neighbors. Okay, so I have connected these lines, and now I have divided these lines. Okay, now in this way what I draw unit cell. Unit cell means any cell which when repeat itself can create a crystal. Now if I repeat this cell, one atom, okay, so this can create a one dimensional crystal. Okay, this is the building block. This unit cell is the building block of one unit crystal. So this type of cell is called Wigner-Lattice cell. Okay, Wigner's lattice cell, and the volume of this Wigner's lattice cell is called your billion joule. Okay, so now you can give one more definition. The volume of Wigner lattice cell in reciprocal lattice, okay, is called billion joule. Now this distance between two atoms is 2 pi by a. So half of this one, pi by a and pi by a. So I'm taking center, this will be minus pi by a. So this region plus pi by 2 minus pi by 2 is called your billion joule. Okay, and another in terms of k, what you can say, the region where we are getting k which have unique solutions. Okay, okay, for of our this thing, unique wave vectors which contain only unique wave vector, that region is called your billion joule. So if we know the properties of this unit cell, okay, we can know the properties of whole crystal, because any property which depend on k, okay, that is periodic. So if I calculate the properties in this region, I can know the symmetry, by symmetry I can know the properties of all the crystals. Okay, that's why we study always billion joule. Okay, so only we are only focused on this small regions. Okay, once you know this small region, we can know all thing about the crystal. Okay, that's why this come the concept of
Sir,
billion joule comes. Yes,
sir, this Wigner one concept, can you just repeat once more?
Wigner's lattice cell, that is a unit cell that is drawn in the lattice. Okay, and how to draw the lattice? Okay, you take an atom and you put a line to nearest neighbor. Okay, and the nearest neighbor distance you have to divide half. Okay, you have to cut it at half. Okay, for example, suppose I have a this my atom, here I have atom, here I have atom, here I have atom, here my atom, here atom. So what I'll do, I will connect this atom with nearest neighbor, this lattice point. Okay, and then I will cut these lines by half, and I draw this one, these lines. Okay, so this is my WS cell, Wigner's lattice cell. Okay, and this cell will be closest to any lattice point. Okay, so this cell is closest to this lattice point also. Similarly, if I draw a Wigner cell here, this will be closest to this one also, this one also. So this will be closest to this one also. So Wigner's lattice cell is always closest to a lattice point. Okay, the unit cell, I told you, what is unit cell? Unit cell is the cell which is the building block of a crystal, when it repeat itself, it can create the whole crystal. Okay, now unit cell can be primitive and non-primitive. Primitive unit cell means which contain only one atom. Okay, that is called primitive unit cell. So Wigner's lattice cell is a primitive unit cell. Okay, which contain only one lattice point. So suppose I drawn this lattice. Okay, in this cell only one point is there. So this is the primitive Wigner's lattice cell is a primitive cell. Okay, and the volume of this primitive cell in reciprocal lattice, not direct lattice. You can draw Wigner's lattice cell in direct lattice also, but the volume of the Wigner's lattice cell in reciprocal lattice, that is called your billion joule. Okay, so I gave you 3 definition. I hope the billion joule concept is clear. And finally, I have to write. Just बोलिए.
Wigner lattice cell वन एटम उसमें नहीं होता ना, यूनिट सेल में वन एटम होता है ना.
तो वन डायमेंशन की यूनिट सेल तो यही है ना. वन डी लेटर्स की यूनिट सेल कैसे बनेगी?
हाँ सर, लेकिन मतलब इसमें भी ऐसा ही होता है, सेल में वन एटम पर.
that is also primitive. Primitive cell का definition यही है, there should be one atom per unit cell. Okay,
नॉट सर, नॉट प्रिमिटिव. Wigner lattice cell जो हम बोल रहे हैं ना, उसमें भी ऐसा ही होता है क्या, वन एटम पर यूनिट?
so that's why I'm telling Wigner's lattice cell is a primitive cell.
हाँ, यस,
तो वो भी primitive cell ही है. Okay, but that is drawing is different. Okay, that is closest to every lattice point. That difference between a primitive cell, that is a non-primitive cell, primitive cell, and a Wigner's lattice cell. So okay, so Wigner's lattice cell is also primitive cell. It's also contain one. Okay, now let me finally put one statement. Okay, which will clear you why we generally need billion joule in solid state. Okay, so all the physical, you can write down all the physical. Okay, all the physical properties, okay, all the physical properties of one-dimensional crystal, one-dimensional crystal that depends, okay, on the k, on wave vector k, okay, must be periodic, okay, with 2 pi by a, okay. So now that is billion John, okay. Now today our aim is to what? Yesterday I told you that k values are there and these k values are not continuous, okay. So here whatever these k values are there in this billion John, okay, these k values are not continuous, okay. So k are discrete, k value, k discrete, k are discrete, okay. And each k is one mode, each k is solution, each k is mode. So now we have to calculate how many modes are present in 1 billion John, or how many modes are present in billion John, how many k values are present, okay. So that we have to
Sir,
calculate.
what is meant by mode?
Mode means how my, okay, let me explain now. Shall I erase this one? Okay, now what do you mean by mode? Mode means how my wave is propagating, okay. Okay, so suppose I have this crystal, okay. So in this crystal, say this is my end point, so my wave can be like this, okay. Suppose this is my distance, say L, okay. So in this case, what is my wavelength? What is wavelength? What is wavelength?
L.
हाँ, अरे wavelength ऐसा होता भाई, तो ये half है 2L. 2L, okay. So this is my so this is my one way of propagating, okay. If my energy is low, my wavelength will be high, so my wave will propagate in this way, okay. So this is one mode. Now so this is 1 2 3 4 5 6 7, no? So suppose now if I draw like this, what is my wavelength now? What is my wave? L, okay. Now my wavelength is L. So this is also so now, so if so this and this wavelength is a higher energy than this one, because the shorter wavelength, the wavelength is shorter means energy high. This is one mode, okay. This is second mode. So in this way you can create any a number of modes, okay. You can keep on drawing wavelengths, okay. You can keep on drawing wavelengths and you can get different wavelengths and each lambda is related by k. So k are also distinct. K are also distinct. So that's why I told you each k value is equal to a mode. Each k is representing energy. Each k will represent a wavelength. Okay, that means each k have represent a vibration of different frequencies or different wavelengths. Okay, I hope your point is clear. What is the mode? Okay, now this mode can be continuous. You can define an infinite number of k, but this is not possible in the case of 1D lattice. Continuous, you can continuous, you can k can be any continuous, you can keep on reducing wavelength, okay. But in general this doesn't happen. In the case of one-dimensional lattice, these k's values, these modes are limited. That's why k values are limited, okay. So let me write here what is mode, okay. So number of modes is equal to number of k values, okay. Now let me calculate those things, okay, using boundary conditions. Put the heading boundary conditions. Okay, Now, boundary conditions also can be two types. One is called fixed boundary condition. Okay. And other is called your periodic boundary conditions. Okay. So in solid state physics, generally we use this kind of periodic boundary conditions. Okay, we rarely use this fixed boundary conditions because fixed boundary conditions shows standing wave. Okay, so let me discuss first fixed boundary conditions, and then we will discuss about this your periodic boundary conditions. So what is fixed boundary conditions? Okay, so we have a lattice. Okay. Okay, let me draw one more atom here. Okay, so I have a lattice, okay, of length A. Okay, consider a lattice, one dimensional lattice of length L. L equals to NA. Okay, so this is the A, this is A. Okay, so 1, 2, 3, 4, 5, 6. For example, this is the length of this lattice which I done. This is 6A. Okay, and it contains how many atoms? How many atoms are there? 7. Okay, so if I consider length n equal to Na, there will be n plus atom. Okay, so this is the a chain of n plus 1 atom. Okay, now these points are fixed. These points are fixed. Okay, these points are fixed means the amplitude of like rope, hai na? We have fixed the end points. So once we have fixed the end points, the amplitude at these points. Okay, so say this is my 0 atom, this is one first atom, this is second atom, third, fourth, fifth, sixth. Okay, or if you n atom, this will be your n plus 1 atom. So the vibration of end points, okay, vibration of end points are fixed. The vibration end point is 0. Okay, now whatever wave we have formed, that will form a standing wave. Whatever wavelength you make this wavelength, or you make this wavelength, these wavelength will vibrate in one position. That means they will not carry any energy. Okay, that's why we don't consider fixed boundary condition in solid state physics. So standing waves means that waves which do not carry energy. So wave vector do not have any direction. Okay, only wave vector is not vector. It's only to have a magnitude, because you have different modes. So you have only wave values. Okay, so for fixed boundary conditions, okay, so this I'm solving for fixed boundary condition. So you can put now the heading fixed boundary conditions.
Sir,
Yes.
can you explain what is standing wave?
Yes, 1 minute. Fixed boundary condition. Okay. So
Sir,
standing waves are the waves which do not carry any energy. They are simply vibrating. They are not traveling waves. Okay. So suppose here these points are fixed. So suppose this is wave. This will be vibrating only this position. They will be vibrating. So this is the wave. Okay, so this is the wave. So this amplitude, they are only one place. They are vibrating. The wave is not traveling. Okay, so because the wave will come. Okay, here wave will come, and it will reflect it, and at this one. Okay, so they form standing waves. Okay, they will vibrate only one positions. They are not traveling waves. Okay, they do not carry energy. But in solid, our waves carry energy. No? Suppose I have a solid, I have a heat this place, and this this heat will come here. Okay, if I hit some hammer, so sound will come also here. Okay, that means we should be interested only traveling waves. Okay, but so this is the हाँ बोलिए.
So but in solid also they don't travel ना sir.
तो अभी यहाँ अगर if I heat here sample, तो heat यहाँ पे नहीं पहुँचती क्या?
ऐसे heat पहुँचता है.
तो energy पहुँचती है ना?
Yes, energy.
तो energy कैसे पहुँचे? Standing थोड़ी energy पहुँचाएगी. Traveling wave तभी तो energy पहुँची वहाँ पे.
सर एग्जांपल क्या है स्टैंडिंग वेव का?
Standing wave का मतलब जो एक ही जगह पे अगर तुम किसी water में if you pull some pebble, that will vibrate in one position ना?
सर like example
Example I'm telling you how what is standing wave. Any fixed rope, the waves you create in any fixed rope. Okay, like you've done in your first year, you have done Meldy's experiment. Okay, so you tie 2 points in fixed, and you in the rope you will create the this waves. Have you done the experiment, Meldy's experiment in your lab?
Yes, I have done, sir.
So that is example of standing wave.
There in the end, there is a longitudinal also transfer wave experiment. So they are standing waves.
That can be both. Okay, longitudinal transfers. Okay, here we are discussing. We will also discuss both the things. Okay, so standing waves means which are not carrying any energy. Yes,
Sir, if they do not carry energy, then conservation of energy means how energy is lost means.
Energy conservation is different thing. Energy carrying is different thing. ना carry conservation से क्या मतलब है? Okay.
तो सर हम जब वेव प्रोड्यूस करते हैं तो एनर्जी तो देते हैं ना.
तो वो वाइब्रेट तो कर ही रहा है ना. उसके पास एनर्जी तो है ही ना. वाइब्रेट तो कर ही रहा है ना. एनर्जी ट्रेवल नहीं कर रही है. उसके पास एम्पलीट्यूड चाहिए उसके पास में. ओके. एम्पलीट्यूड है तो एनर्जी इन क्लासिक wave energy is proportional to amplitude square. Okay, so now, okay, so when the end points are fixed, you got standing waves. Okay, now for standing waves, okay, what you can write? So what is the equation for standing waves? Can anyone tell what is the equation for standing waves?
Y is equal to y naught sine.
Okay, so you can write u naught sine or a sine kx, or u naught, you can write u naught. Okay, sine kx and sine omega t, isn't it? This is standing wave solution. Okay, standing wave. Now my end points are same amplitude. That means I can write the point mu 0, okay, and atom mu n. Okay, so this is 0 atom. Okay, and this last atom is n atom. 0 plus n, total n plus atom. So these 0 atoms and these two atoms have same amplitude, equals to what? 0, because now these endpoints are fixed, so they're not vibrating. So I can write u naught equals to 0. Okay, now what is un? You already know what is un. So what is un? What is un?
So displacement of nth atom.
A exponential iota k na minus omega t, isn't it? Okay, put it equal to 0, and find out the k values. Okay, so here we are writing, sorry, here we are writing in a, this is as a standing wave. So my un will be what? U naught sine k na, okay, sine omega t. Okay, and u0 will be simply 0, and put it to 0. Okay, so this will give me sine k, last atom is n. Okay, so na equals to 0, and you can write sine m pi. Okay, so here you can write k equals to what? Sine m pi. Okay, sine m pi. So where m is what?
M pi upon na.
Okay, so this will be kna is equals to m pi. Okay, and your k will be simply m pi upon na. Okay, and here m is what? M is your 0, 1, 2, 3, so on, only positive values. Okay, because these are standing waves. Okay, so for standing waves we will not take minus values, because they are not moving anywhere, direction is not there, only amplitude is there. Okay, so here also you can write one point. Okay, for fixed boundary condition, that will be used several times in solid physics course. Fixed boundary condition, k values are positive. Okay, we won't take negative k values in the case of standing waves. Okay, now if I put the values here, I can get k values how much? 0, then I get pi by na, then I can get 2 pi by na. Okay, then I get how much? 3 pi by na. Up to how much I need to go? I am calculating that this modes in billion John, और billion John की boundary कहाँ पर खत्म होती है? Pi by a पे. Pi by a पे. So I will go up to what? N pi by na. So n cancel. So k will be pi by a. Okay. That means in standing wave solution, we are only taking positive values of k. Okay. So I'm going up to here, up to pi by a. Okay. So now let me discuss you further. Okay. Now this is my first atom. This is fixed. Okay. And this is my last atom, n+1 atom. This is also fixed. They have zero amplitudes. Okay. K0 means nothing, na? No solution. K0 means what? So solution is 0. So how many unique solutions you are here? How many unique K value are here? Can anyone tell me?
n+1.
n+1 or n-1?
So you are not including pi by a?
But total we have n+1, na? 1, 2, 3, 4 up to n plus total n+1. But these two values are fixed, na? I told you this. These and atoms are fixed. These are fixed. These are fixed. Okay. That means only we have, so that I can write k equals to what? Pi by Na. Na is a lattice. L equal to Na. 2 pi by L. 3 pi by L. Okay. Up to what? N minus pi upon L. So these are your unique k values. That means there are n-1 modes. Very good. Okay. That means in fixed boundary conditions. Okay. In fixed boundary condition. Okay. You have n-1 distinct k values. K values. Okay. That means that is the number of modes is equal to n-1. So how many lattice points are there? That much modes will be there. Okay. Now, shall I raise this one? So n-1. Okay. So this is what? This is when? This is in fixed boundary condition. n-1 kab hai? And you have fixed boundary condition. Now n is very large. Okay. N is very large. In our crystal, n is very large. So you can assume n-1 is equal to just n. Jitne bhi, so the number of modes equal to number of lattice points. How many lattice points are there? Okay. The simple thing is, okay. The number of modes, I can write number of modes is equal to number of lattice points. Okay, of course n-1, but you can neglect n. Okay, so this was your fixed boundary condition. Okay, now let me solve this for periodic boundary conditions. Okay, similarly we can do it for now for periodic boundary conditions. Periodic boundary conditions. And let me clear one more thing here. Here, the interval between two k values, delta k, is how much? Pi by L. Okay. That delta k is what? Pi by L. So delta k is pi by L. So delta k is what? Volume of one mode. Okay. In between two k values, that is difference of delta pi L. Okay. Delta k is what? Delta k is equal to volume of unit cell. Volume of k cell. Okay. Volume of k cell in 1D. Now here one dimension, that's why we're taking length. Okay. So delta k means delta k pi by equal to pi by L is this is a one mode. Okay. So this means delta k range we have one mode. Okay. So in unit length, in unit k range, how many modes will be having? We are having unit k range. We'll be having 1 upon delta k modes. Okay, 1 by delta k mode. That means what? L upon pi modes. L upon pi modes. Okay. Now there comes the definition of density of state. What is density of states? Please switch off your mic. Okay. Density of state. Okay. Density of state is defined number of modes. Number of modes. Okay. Per unit range. Per unit range of K. Okay. Is called density of state. Okay. The number of per unit range of K is called density of state. Density is very important concept. Okay, we are soon going to come on this topic, density of states, in detail. Okay, now shall I erase this one? So I'm erasing this.
Density of his states don't erase.
So I'm erasing this one. Okay, so now density of state. Okay, density of state generally you can write by dk or ge. Okay, density of state is equal to what? L upon pi in 1D. Density of states in 1D is equal to L upon pi. Okay, or you can write dk equal to L upon pi dk. Okay, so this is the for fixed boundary conditions. This is the density of state, fixed boundary conditions. Okay, this is the density of state. Now if you want to convert, you want to write in terms of frequency d omega. So simply you have to divide L by pi dk by d omega into d omega. Okay, so sorry, you want dk. So it's okay. So now you can write L upon pi d omega, and dk by d omega you can put down, and this is your what? L upon pi d omega, and dk by d omega nothing. This is a group velocity. Okay, the group velocity. So this formula also important formula.
Sir, in third step on left hand side, have we are multiply by d omega, or we have changed complete function?
Yeah, so now this is written in terms of k, na? Now I want to write
Yes.
this function in terms of omega. Like I
Omega.
multiple k, I could have multiplied by omega also up here. Okay, so if I want to write in terms of omega, okay, so I would to convert this function also. Okay, so I put d omega, so that will cancel, and now dk upon d omega, that is your group velocity, and one for 1D atoms at k tends to 0, group velocity and phase velocities are same. So instead of writing group velocity, you can also write here phase velocity also. Okay.
So we have used formula which gives relation between omega and k.
Yes.
And then that substitution d
Yes.
k is equal to d omega.
Yes. Okay. So density of state is also density of state in terms of k. This is density of state in terms of omega. And you can also write density of state in terms of any other variable. You can change the variable also. You can write density of state in terms of energy also. Okay, that is the most common way of writing density of state in terms of energy. Okay, so this was your fixed boundary condition. Okay, now quickly let me finish the periodic boundary condition. Okay, so periodic boundary condition means now you have this lattice. Okay, now what you are doing, instead of making this standing wave, you're saying, because my crystal is so long, okay, and crystal is so long, that means when wave are traveling, so its boundaries are not affecting my waves. So I have a traveling type of solution. So instead of taking a straight line, now I am taking, so earlier I took 7 atoms. Okay, now I am taking that, I am just taking this one, I am making a ring. Okay, out of this lattice I am making a ring. Okay, so this is the ring. Okay, so say I have 9 atoms, so say this is n equals to 0 is 8. Okay, suppose I have 9 atoms. Okay, 1 2 3 4 5 6 7 8 9. Okay, so this is a linear chain. Okay, of Na, linear chain equal to Na atoms here, and n equal to 8. Okay, is A. So now I am making this wave as a in terms of ring. Okay, so now what I'm telling, the amplitude of this atom and this atom same, it's not 0, because now it is ring. Okay, so in crystal I have some wave, Okay, some other point also we are having same wave which have the same amplitude. We can have some points where crystal is vibrating. So in crystal there may be some points which have equal amplitudes. Of course possible. There may be any points where you have equal points. Okay, so I am taking now those equal points. Okay, now I'm not taking end boundaries. I'm only taking the where the amplitude is same. So applying periodic boundary conditions. Okay, so now this is now if you apply, I hope my point is clear. Okay, I am taking a ring. Okay, now if I apply periodic boundary conditions, okay, so I can write my atom 0 and 0 plus n, their magnitude is same. Okay, so if I want to write now my mu, okay, mu n as a exponential iota k na minus omega t. Okay, so if I want to write kn, so I can write kn. Okay, k na, capital Na, un equals to u0. Okay, u0 is what?
Excuse me, sir.
हाँ
Sir, small n is equals to 0 लिखा है आपने?
नहीं, so ये 0 plus n.
सर ये फिगर में small n is equals to यहाँ पे 8 लिखा है.
हाँ यहाँ पे 8 लिखा है. If you want say total atoms are n, okay, you can write total atoms. What is the problem? The symbol na. If total atoms are, this is not I am just giving an example. If there are 9 atoms, actually they are long chain. Okay, so that will be say capital N is 8. Okay, so you can write now u0 equal to u0 plus n. Okay, now if you put 0 here, so this will be 0. You will be having only e power minus omega t. Okay, now both amplitude are same. It will cancel. Omega power also cancel. So you will get what? I equal to k na equals to 1, and at 1 you can write iota 2 pi. Okay, this term is cancelled. So you get 1. Okay, that is equal to e power iota 2 pi, and that is equal to what? I k na equals to what? 2. You can even write 2n pi. 2n pi or 2m pi, n we are using here, so you can write 2m pi here. 2m pi. Okay, so this will give you what? Iota 2m pi. Iota cancel. Okay, so what you get? K equals to what? Now m here can take any values. Okay, yeah, n can take any number value. Now here how many atoms are there here? Here atoms are n. Okay, so 1 2 3 4 5 6 7 8. Okay, so 0 or 8 are combined. Okay, we are making them together. We're counting n atoms only one time. So instead of now you don't have n plus 1 atom, you have n atoms only. Okay, earlier this 1 2 we have n plus 1 atoms. Okay, now this atom reduced because we are these are same atom, because they are same amplitude. We are connecting them like this. Okay, so we have only n atoms. Okay, so now your m can have 0 plus minus 1 plus minus 2 plus minus 3. Okay, it can have a negative value also. So my k can have, okay, what value? 0, 2 pi by L, okay, 4 pi by L, up to what? Up to what? Pi by L, up to what? N by 2. This is Na. See, I'm writing here Na. Now k can go up to only pi by A. Okay, so this should be n by 2. Okay, but this is now plus minus. This is now plus minus. So n by 2 atom, total atom become n. So now how many values we have? K values. Okay, I hope you are getting what I'm saying. Okay,
yeah, हम plus minus क्यों ले रहे हैं?
because now this is a traveling wave. Okay, it can go through this way, it can go to this way. Earlier it was standing wave. Okay, that's why I'm repeating so many times. Children getting standing waves. That wave is not moving anywhere. So wave vector is a scalar. It don't have a direction. Now you have a traveling wave. Your wave can move left. Wave can move right. Okay. So now k is a real wave vector. Okay. So now you have both the directions. Okay. So now you have plus minus
Sir?
value. हाँ.
Sir, last वाले term में 2n क्यों आया है denominator में? k equals to
यहाँ पे
सर ऊपर 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 k equals to जहाँ पे लिखा आपने लास्ट वाले में
लास्ट वाले में and so if you can now you cancel n by n, so you want to go up to how pi by a na, so this is what 2 pi by a, so what are we getting? We are getting 2n pi na, 2 pi 4 pi 6 pi, okay, like this. So here n should be what? N by 2, so n 2 to cancel, okay, n cancels, you get pi by a. Here terms are coming what? 0 2 pi 4 pi 6 pi, okay, like this terms are coming. So I'm writing here, you can write here n, this n by 2, so plus minus n by 2, this will be, you can calculate total number of items are n.
नहीं सर नीचे 2na क्यों आ रहा है
यहाँ पे
डिनोमिनेटर में? नहीं उसी में डिनोमिनेटर में 2na क्यों आ रहा है?
सारे टर्म्स में na है ना, और
भी-
लास्ट के टर्म में सिर्फ 2
भी-
फैक्टर अलग है।
तो मैं पूछ रहा हूँ यहाँ पे n कहाँ तक जाएगा इस टर्म में? अभी छोड़ दो, ये आप छोड़ दो, ये आपका ये वैल्यू आ रहा है 2 पाई आ रहा है, na आ रहा है, ये तो सब जगह आ रहा है ना 2 पाई करके। अब ये एटम कहाँ, ये वैल्यू कहाँ तक जाएगी, ये नंबर कहाँ तक जाएगा?
कैपिटल एल तक।
कैपिटल एल तक जाएगा, तो फिर ये रेंज क्या हो जाएगी? 2 पाई बाई ए हो जाएगी ना, के की वैल्यू, के की रेंज क्या, के की रेंज क्या है?
प्लस माइनस पाई बाई।
हाँ, तो n by 2 तक जाएगा ना, तभी तो कैंसिल होगा पाई बाई ए। सो वी वांट k रेंज अप टू ओनली अप टू प्लस माइनस पाई बाई ए ना, ओके। सो ये वैल्यूज, ये 0 2 4 कहाँ तक जाएगा? n by 2 तक, ओके। भी यहाँ पे 1 है तो 2 पाई है, 2 है तो 4 है, तो लास्ट टर्म होगी तो उसको 2 नहीं आएगा क्या? आर यू गेटिंग माय पॉइंट? ये 1 है तो 2 है, 2 है तो 4 है, 3 होगा 6 होगा, 4 होगा तो 8 होगा, n होगा तो 2n होगा, okay. So that means you have now total n number of modes equal to what? Number of modes equal to number of distinct k values, okay. You can write up to n here, and then you say that we will not take this minus value because they are equivalent. Like this also you can tell, okay. So number of modes equal to number of distinct value. Now in this case, what is happening? I have a 0 here, n by 2 atoms this side, n by 2 atoms at this side, because this is a periodic wave, okay. So total number of modes, how much? N by 2 plus n by 2 to n by 2. Total number of modes is again n. Earlier we are getting number of modes equal to n minus 1. Okay. Earlier we are getting number of modes equal to n minus 1. Now here number of modes is equal to n. Okay. So this is what? This is in periodic boundary condition. Periodic boundary conditions. Okay. And if I take delta k, okay, na equals to n, so 0 2 pi by l plus minus 4 pi by l, okay. Similarly you can keep on going. Now the difference between two k values, delta k is 2 pi by l in fixed boundary conditions, okay. And if I want density of states, okay, density of state is just 1 by delta k here in one dimension. How many states? Number of states. So this is the volume of one unit cell, okay. So this is what? Volume of one unit cell in 1D, okay. Now similarly, if I want to write now density of states, so density of states, okay, dk will be now, instead of l pi, now will be l upon 2 pi. That will be in periodic boundary condition. Periodic boundary condition. But the number of modes are same. तो यहाँ पे physics change नहीं हो रही है, okay. Just there different way of representation, okay. If are calculating number of modes, okay, number of modes तो हमेशा यहाँ पे भी n आ रहा है, वहाँ पे भी n आ रही है, यहाँ पे n आ रहा है, तो physics change नहीं हो रहा है, दोनों boundary condition equivalent ही है, okay. So we will discuss more about when we will do calculate density of states. That time we again see what is the difference between this fixed boundary condition and periodic boundary conditions, okay. So there is only there is only change of factor of 2, Okay, in fixed boundary condition you have a k value always positive, and here you can have a negative values. That means k can have a minus k to plus k. There you can have a 0 to k. Okay, so whenever I take the calculate the range in a periodic boundary condition, I will multiply by 2. While if I use the fixed boundary condition, I will not multiply by 2, but the answer will come always same. Okay, we'll see that one. Okay, so let us give some 2 minutes break. Okay, not more than 2 minutes. Just take the water and come back again. We'll do other things. Okay, so I'm erasing this one. This was your 1D monoatomic chain. The question based on this topic. Finding any difficulties. Okay. So now I'm going to do. We have done one atomic chain. Now I'm going to do diatomic chain of lattice. Okay. Adding diatomic lattice chain. Diatomic lattice. Diatomic one-dimensional lattice. One-dimensional lattice. Now here, what do you mean by diatomic? Okay. Now we have here chain of atoms. Okay. Earlier we were having monoatomic atoms. Okay, one atoms. Now we have two atoms at each lattice point. Okay.
Sir, here one is big and one small.
Yeah, yes, one is big, one is small. Okay. So now I am taking a diatomic chain. Okay. Where we have mass m1. Okay. And here this mass is m2, and mass m1 is greater than mass m2. Okay. So m2 equal to, you can write that is small m. Okay. And we have this atomic chain. Okay. So I'm keeping distance again, lattice constant as a, okay, like we have done yesterday, so that my billion zone boundaries will not change. Okay. So now this distance is say a by 2. This distance is a by 2, and the lattice constant is again I'm keeping a. Okay. Now because now there are two atoms. Okay. So say this is my atom number 2n. Okay, this is my 2n atom. Okay, this is 2n plus 1. Okay, or 2 small n, you can add 2n. This is my 2n plus 1. This is 2n plus 2. Okay, this is what? This is 2n minus 1 atom. This is 2n minus 2 atom. Okay, now again, these lattice I can assume connected by springs. Okay, these are springs. The springs, distance is a by 2. These are springs. These all are springs.
Why you have taken
Huh?
distance equals to 2n minus 1?
Which one?
So this
Now we have two atoms now. So earlier we are taking one dimension, we are n atoms. Okay. Now where n is coming, now 2n will come now. Because now number of atoms double, number of atom become double now.
okay.
Okay, if I want to get the position, agar मेरे पास पहले पास n atom, now that atom will be 2n atom. Okay, so this will be my 2n atom. This will be 2n minus 1 atom, 2n minus 2, 2n plus 1, 2n plus 2. Okay. Okay, so this is my case. Now if I give some amplitude to this atom, okay, so the amplitude will be what? U2n. Okay, so this spring will be similarly, the amplitude of this atom will be what? U2n plus 1. Okay, and similarly the amplitude of this atom will be what? U2n minus 1. Okay, and so this is your nth atom, this is n plus 1 atom. Okay, now I want to write force. Okay, now I want to write the force on 2n, this bigger atom. Okay, so I am writing all the bigger atom as an even number. Okay, and the smaller atom is the odd number. Okay, so now let me tell what is the force on 2n. Like yesterday we calculated, the spring constant is beta. Okay, so what is the force on 2n? बताओ कितना आएगा?
Beta
U2n
into
plus 1.
U2n minus 1 minus
Beta, then
into U2n minus 1.
U
you 2n minus 1. No.
2n plus 1.
2n
2n plus
2n
1
plus
minus
1.
Yes,
U2n.
yes. We have to take, if I want to take calculate the force, I will take these neighboring atoms. Okay.
Yes, sir.
So this is this neighboring atom, this one neighboring this one. This is so U
2n plus 1
plus 1 plus
minus U2n.
minus 2un. Isn't it?
Yes, sir.
Correct? Just check yesterday's solution. If I want to force on this atom, I will take these two nearby atoms, because we are considering nearest neighbor distance. The force on 2n is beta U2n plus 1 plus U2n minus 1 minus 2un. Okay. And similarly, if I want to calculate the force on 2n plus 1 atom, what I will write? Okay. This nearby atoms. Okay. So that is U2n plus 2 plus U2n, okay, minus U2un plus 1. Okay. Ardex, these expressions are clear to you?
Sir, there is a minus sign before beta, right?
Yesterday,
Yeah,
check.
sir, we have taken yesterday.
There was beta minus beta. Okay, you can put beta minus beta here. Okay.
Minus beta x,
Yes, sir.
we have seen restoring force.
Okay. So this is the expression. Okay. Now I can erase this one. Okay. Now you just write solutions. Okay. The way yesterday we have written the solutions. Okay. So now solution, how can we write U2n? If I want to write U2n, what I write? A exponential iota k. What should I write? 2n. And yesterday we were writing na. Now instead of a, what? A by 2.
Yes, sir.
Okay. So now see this is a by 2, 1a by 2, 2a by 2, 3a by 2, 4a by 2, 5a by 2, 6a by 2. So wherever reaching, that is a by 2. So this is atom is position 2n. So this position is from 0. If we take the position of this atom, that is what? 2n a by 2. Okay. So na. So that is same. So now the lattice constant is a by 2. The distance between 2 is a by 2. So 2n a by 2 minus omega t. Okay. So this is the your un for 2n. Similarly, now these atoms are not same. Okay. Now if I want to write u2n plus 1. So one is bigger atom and other is smaller atom. So their vibrations are not same. अलग atom है ना. एक का mass ज़्यादा, एक का mass कम है. So if you give vibrations, so they will not vibrate with same amplitude. Okay. So I will take the amplitude of a small atom as a b. Iota k. What is 2n plus 1? 2n plus 1. A by 2 minus omega t. Okay. Similarly, you can write now for 2n plus and 2n minus 1 also you can write same way. Okay. So now write 2n minus 1. Okay. Now you write u 2n minus 1 and 2n minus 1 is again your smaller atom, different atoms for is also b exponential k 2n minus 1 a by 2 minus omega t, isn't it? Okay. So this become, now you can calculate what is your force on F2n. Okay. Similarly, here you want U2n plus 2. Okay. So you have U2n, we have done U2n plus 1, we have done. You want to write U2n plus 2. U2n plus 2 is again even number. That is the larger atom. So you can write A exponential K 2n plus 1. Okay, 2n plus 1. So 2n plus 1 a by 2 minus omega t. So now you have this expression.
2n plus 2 आएगा ना?
2.
Sir, it is 2n plus 2, no?
Yes. Thank you. Okay, now you have the expression. Just put it the values here and find out the equations. Very simple. Okay. Now, if I want to write, say, force F.
And the omega value will be same for each of them.
Yeah, because vibration is the same here, no? If they're vibrating, they're vibrating together. Okay. So frequency I'm taking same. Okay. So this is only amplitude will change. Okay. So this 2n. So 2n will be what?
Sir,
mass.
vibrations are not same, na? Vibrations.
Their amplitude is not same. They cannot have independent like this, na, vibrations. Okay. If they are vibrating, they have some motions. Okay. So the motion is one, na? So the motion is one. Their frequency will be same. One motion cannot have a two frequency, na? There can be different modes. Okay. Only their amplitude are different. Okay. So it's for smaller I'm writing B, for larger I'm writing A. So the amplitudes are different. Okay. So we'll see now what happens. Okay. So now mass is M. Okay, M1. Okay, I have given mass M1, M2 na. So M1 d2u dt square. Okay, put the values here. This is minus beta. Okay, u 2n plus 1 plus u 2n minus 1 2 u n. Okay, now just put the values what we have written here. Okay, now I'm getting F2n. So this will be M1. Okay, u2un. If you differentiate 2 times, what will get? Minus omega square. Okay, and same you get again A exponential iota k na minus omega t. Okay, and here minus beta u2n plus 1. This is you get B iota k 2n plus 1 a by 2 minus omega t. Okay, k minus omega t. Okay, similarly you can write for 2n minus 1. Okay, so you be 2n minus 1 is again my B atom. Okay, B atom. So B e power iota k 2n minus 1 a by 2 minus omega t. Okay, and then last we have this one 2un u2n my A atom. So 2a exponential iota k na minus omega t. या ऐसा अपना अपना करो, ठीक है ना, no need to check, okay, you have to do yourself then already. So now minus m1 omega square, okay, a, now divide by this factor, so this become your 1 here minus beta here, okay. If you divide by here, okay, so what will be remaining here? You will be remaining here beta, this is n, so n it cancel, so only exponential iota k by 2, okay, and here you will be writing b e power minus iota k by 2, okay, and then you will be having here what, only 2a. So if you write this way, okay, so I'll get what, minus m omega square a, okay. If I take this b common, so minus beta b iota exponential k a by 2 plus e power minus iota k a by 2, okay, and then I have a minus 2a beta, okay. So now I'll take this a there, okay, so I'll make the equations, okay. So if I take a there, okay, so what will come? So final equations I'm writing now, you will tell me whether it is correct or right or not, okay. So now I can write, okay, so now I can write this equation. Kara, what equation is coming for you? Okay, so I can write this become positive 2 beta minus m omega square, coefficient is a, okay. Similarly, I can write here 2 beta, this I can write as a what, cos k by 2, 2 cos k by 2, so I can write this is 2 beta b cos k by 2 equals to 0. Are you getting this equation? Into b is there already, 2b cos ka by 2 b. Okay, this is my equation number 1a. Are you getting this equation? Or you're not solving, just copying?
Yes, sir.
You're getting this equation, huh?
Yes, sir.
Okay. Now this is we got first equation. Similarly, you can get the force on 2n plus 1 atom, and similarly you write the equations, okay, and let me know what equations are coming.
सर ये लेफ्ट साइड पे 2 बीटा प्लस m ओमेगा स्क्वायर है या माइनस है?
कहाँ पे?
सर इधर लेफ्ट साइड पे लास्ट पार्ट में
इसमें 2 बीटा माइनस m ओमेगा स्क्वायर a, यहाँ से
यहाँ पे माइनस बीटा, यहाँ पे माइनस 2a बीटा जो किया है ये पूरी ब्रैकेट में था,
तो यहाँ के प्लस नहीं हो जाएगा क्या? इसको इधर लेके आ रहा हूँ मैं, तो ये प्लस
वो वाला बीटा कॉस बीटा वाला टर्म भी फिर प्लस में आएगा,
तो फिर कॉस अच्छा कॉस बीटा प्लस में आएगा
सर, सारे माइनस कैंसिल कर देंगे फिर।
एक मिनट चेक करने दो मुझे।
बाहर माइनस बीटा कॉमन था,
just wait
अंदर माइनस 2a था।
just me write the equations, okay, so I have minus m omega square है, so ये बीटा तो आपने लिखा है ना मुझे माइनस बीटा, तो ये एक्चुअली ये लास्ट का देखो बीटा था, माइनस था कि नहीं था उसमें लास्ट वाले में?
सर दोनों तरफ माइनस था, फिर कैंसिल हो गया।
नहीं जैसे माइनस बीटा था, ओके माइनस बीटा था, देन
माइनस बीटा था, बाद में वो चेंज करके कल हमने किया था।
हाँ
वो कॉस स्क्वायर आ गया था, वो साइन लेके
एम ओमेगा स्क्वायर आया था। तो लेट मी चेक, यस्टरडे हमने क्या किया था, माइनस बीटा किया था इसको, तो un प्लस 1 F and force equal to minus du and dn, so this came minus, okay, so minus cancel, no just check it, okay, because I am getting solution like this only, okay. अब क्या माइनस का मिस्टेक कहाँ पर हुआ है, what I am writing my equation as 2 beta m omega square. आप लोगों को क्या आ रहा है चेक करो, अपना अपना कैलकुलेशन करो, बताओ क्या आ रहा है. आई एम गेटिंग दिस इक्वेशन.
Sir, it is M1, na?
हाँ m1, sorry m1, this is m1, this is m1. What you're getting, let me know.
So 2 beta plus m omega square whole a minus 2 beta cos k by 2 b
So,
equal to 0.
तो ये सेम आ रहा है ना,
सर नहीं है, ये वाला प्लस माइनस की प्रॉब्लम हो रही है लेफ्ट साइड. हाँ, इस वाले
ये
2
प्लस
बीटा
है,
माइनस
2
2
बीटा.
बीटा माइनस m ओमेगा स्क्वायर होल
अच्छा,
a.
यहाँ पे प्लस है आप बोल रहे हो.
नहीं सर, इसमें जो पहली वाली ब्रैकेट में टर्म है
इस,
2
इस,
बीटा माइनस m ओमेगा स्क्वायर.
तो ये ऐसा बोल रहे हो,
नहीं
माइनस
सर, 2 बीटा प्लस m ओमेगा स्क्वायर.
प्लस. अच्छा ठीक है, ओके, लिख दो उसको, 2 बीटा प्लस m omega square. बाकी लोग भी चेक करो कितना आ रहा है. बाकी लोग भी
हेलो
चेक करो.
सर,
हाँ
आई थिंक हमारा मिस्टेक यहाँ हो रहा है, d2un बाई dt स्क्वायर, मतलब वो जब करते हैं तब
हो,
डेरिवेटिव डबल लेने के बाद
हाँ
माइनस चला जाएगा ना.
हाँ, तो वही तो मैं कह रहा था, माइनस नहीं आता है, तुम लोग तो दिखाया माइनस मुझे
नहीं नहीं, बीटा में आता है सर, ये
भी. इसको
डेरिवेटिव
करोगे,
में.
हाँ बीटा में कौन सा
हाँ,
आएगा.
माइनस
जब
बीटा भी
इसको जब जब इसको दो बार डिफरेंशिएट करोगे तो आयटा स्क्वायर माइनस नहीं हो जाएगा क्या. यूएन को दो बार डिफरेंशिएट कर, इसको व्हेन यू डिफरेंशिएट 2 टाइम्स, ओके, तो ये माइनस हो जाएगा क्या, ये आपका प्लस हो जाएगा क्या.
सर ये प्लस हो जाएगा,
ये प्लस हो
बीटा
जाएगा, ओके,
माइनस होता ही
ये
रहेगा.
प्लस हो जाएगा, ये प्लस हो जाएगा. एंड देन यू आर गेटिंग, और ये
सिर्फ वही रहेगा सर, 2 बीटा माइनस m ओमेगा स्क्वायर.
ठीक है, चेक करो यार, चेक करो, नहीं तो दोबारा मुझे मुझे देखना पड़ेगा पूरा वापस करके. गिव मी 1 मिनट नाउ, लेट मी चेक इक्वेशंस आर करेक्ट और नॉट, वरना पूरा मैथ खराब हो जाएगा. हाँ ठीक है, इक्वेशन तो ये आ रहा है. Just 1 minute. ओके, सो ये कैलकुलेशन कर लेना. ओके, तो मिस्टेक होगा तो फाइनल आंसर तो मैं लिख रहा हूँ कैसे कैसे करेंगे. सो दिस इज योर इक्वेशन नंबर 1. ओके, सिमिलरली इफ आई सॉल्व अदर वन, ओके, सो फॉर others if I solve, so I will get the equation 2 beta minus 2 beta cos k a by 2, ओके, into a, जो यहाँ पर वो इधर इधर आ जाएगा. ओके, एंड देन फॉर सेकंड आई एम गेटिंग 2 बीटा माइनस ओमेगा स्क्वायर m2 b इक्वल्स टू 0. दिस इज मस्ट बी, जस्ट चेक ये आ रहा है क्या दोबारा आपका. ओके, सो जो यहाँ पे आ रहा था b का कोफिशिएंट, वो यहाँ पे a का कोफिशिएंट हो गया, और जो यहाँ पे आ रहा था a का कोफिशिएंट, वो यहाँ पे b का कोफिशिएंट हो गया. जस्ट चेक इट एंड टेल मी. Okay, now we need to solve these equations. Okay, so you have to do yourself. Okay, now just we have 2 equations, that equation we need to solve. Let me solve these equations. Okay, इसमें कोई mistake हो तो you can check yourself. So we will take coefficients 2 beta, okay, omega square m1 minus 2 beta cos k by 2, okay, minus 2 beta cos k by 2, okay, and then we have a 2 beta minus m2 omega square equals to 0. Okay, if you solve this equation, I'll get 2 beta minus omega square m1, okay, and 2 beta minus m2 omega square, okay, and then this is minus minus plus and minus 4 beta square cos square k by 2 equals to 0. So I should get this equation. Okay. Now just solve this one and make it quadratic equation in omega square omega 4. Okay, so if you multiply these atoms, okay, so omega square this will be omega 4. So I can write m1 m2 omega 4. Okay, similarly if I multiply by this one, okay, this will give me omega square m1 2 beta, and this will give me 2 beta m2 omega square. So I can write m, okay, I can write this is a 2 beta, okay, omega square m1 plus m2. Okay, just I'm multiplying, 4 terms should come. Okay, first term omega square 4. Okay, similarly 2 beta m2 omega square and 2 beta omega square m1, so m1 plus m2. Okay, and finally we have last term is 2 beta 4 beta square. Okay, so this become plus 4 beta square. Okay, already these are 4 beta square cos square ka, so I can write 1 minus cos square ka by 2 equals to 0. Okay, now this is m1 m2 omega 4, so say this is omega 4. Okay, 2 beta, we have m1 plus m2, I can divide by m1 m2. Okay, plus 4 beta square, I had divided by m1 m2. Okay,
Sir, in
and
the second term, omega square will also come.
omega square भी आएगा, omega square भी आएगा. Okay, and this is 4 beta square 1 minus cos square k by 2. What you can write?
Sin square k by
Sin square k 2.
Sin square
k
k by 2. Okay, this is the equation, and divide by, of course, m1 m2. Now the solution of this equation, you know what the solution will be this equation. Okay, if I take equation, this will be what? Minus b upon 2a plus minus b square minus 4ac by 2. This is a quadratic equation. Okay, so now this is omega 4. So instead of equal omega 2. Okay, so omega square will be minus b upon 2a. Okay, so minus this b is this one. Okay, so 2 beta m1 plus m2, okay, upon m1 upon m2 into 2a. So 2a, a is 1. Okay, so 2a, so 2 to cancel. So I'll get beta m1 plus m2 upon m1 m2 plus b square ac. Okay, so b square is again what? B square this one. So this become 4 beta square and 2a. So 4 beta square m1 plus m2 का square and m1 m2 ये भी square ही है and का square. Okay, this is b square minus 4ac. 4a is 1 and c is what? C is this one. So 4 for 16. This becomes 16 beta square sin square k a by 2 upon m1 m2. So this type of expression is coming. Okay, and if you solve further, okay, this will be omega square beta m1 plus m2 m1 m2, okay, plus minus this half go inside become 4. So this will cancel, this become 4. Okay, so what I'll get beta square m1 plus m2 whole square. Okay, or this is whole square m1 plus m2 upon m1 m2, and this we have minus 4 beta square sin square
But it will
K-
come
K-
2 beta, na?
why 2
Because this-
2 go inside, so it will become
Okay,
4 na.
four.
So
Okay.
4 for cancel. Okay, Now how to solve further? Okay. Now what I can do? Okay. So I have omega square beta m1 plus m2 m1 m2 plus minus. Okay. I'm taking this out, beta m1 plus m2. Okay. So beta m1 plus m2 upon m1 m2 I'm taking common. Okay. So inside what will be remaining? It will become 1. This become 4 beta square. Okay. This is square. So m1 m2 come here. Okay. And m1 plus m2 square. Okay. And this will you have
We have taken beta common.
Beta common ले लिया ना, beta square common ले लिया. So 4 m1 m2. Okay. You will be having 1 minus, sorry, this will be sine square k, sine square ka by 2. Just check it what you're getting, this one. Okay. What is it? So anybody? Okay. So shall we stop here, because you people have next class also. Okay. So let me stop here, and tomorrow we'll continue from here. We are here onwards. Okay. Because it will take some 10 minutes more from here. So let us stop here. Okay. So tomorrow. So somebody mic is, please switch off your mic. Okay. So I'm stopping here, and we'll continue tomorrow. We'll see what expression, what dispersion relation we're getting, and we'll also discuss the physics of this. And instead of one atom, we keep 2 atoms per lattice point, how physics changes, how my dispersion curves get changed. Okay. So any question? Any question, students? So I'm stopping here. Okay.
Sir,
हाँ बोलिए.
why we use density of state, sir? What is the use?
Where? See,
Sir?
density of state, what we have calculated today. Okay. Density of state is very important parameters if you want to calculate our system energy. Okay. If you want to calculate system energy, and if you want to calculate specific heat, any other properties of material, for that we require density of states. Without knowing density of state, you cannot do theoretical calculations. So in earlier next chapters, when I'm going to calculate the specific heat solid, okay, for that I need the energy. Okay, once you know the energy, then only you can differentiate with respect to temperature, then only you can know the specific heat. Okay, so in order to know the solids properties, we need density of states. I hope it's clear. Okay.
Yes, sir.
Any other
Thank you,
question?
sir.
Any other question? Okay. So there are no question. So I'm stopping here. Okay.
Thank you, sir.
I will meet tomorrow. Okay.